Well, good day, ladies and gentlemen. This is Dr. Doug the Data Dude, and we're starting our second week on the topic of regression, and now we're going to be finishing up the topic of simple regression, and then later on in this lecture, then we'll begin to discuss multiple regression. So let's go ahead and review real briefly where we were at the last time. At the end of the last time, what we did was we talked about the relationship between correlation and the regression coefficients and the similarity between correlation and regression. We identified the general linear model and its components, namely the intercept, the regression coefficient, and the error. We discussed the principles of least squares, which was basically looking at the relationship between the average or the slope and each individual person's score and taking the square of that difference and the regression equation, then minimizing that difference in order to calculate the linear regression line. Next, we talked about the interpretation of the regression coefficient, its standard error, and the estimate and the calculation of the outcome using the general linear model. And we basically ended at that point with a demonstration of how you could use a regression model in a clinical situation in order to, to identify the mean score of a sample or a population in the 95% confidence interval. But in addition, then, we also looked at the coronary heart disease risk software program that used multiple regression equations in order to predict an individual person's risk of an adverse outcome. So today, we're going to get started by describing the assumptions of the multiple regression equation, to be able to next explain to a colleague the calculation and the meaning of the coefficient of determination, or the R-square, and then to finally to finish up our scenario number 4, looking at the relationship between a change in weight and a change in blood pressure and how that might be interpreted in the literature. So let's move it on. Okay, well, near the end of our last lecture, one of the things that we spent a few minutes talking about was the calculation of the average score or the prediction of the average score of Y within the sample, and how we calculated the 95% confidence interval and for the sample. And then we also looked at how we predict an individual score for an individual patient, and we looked at the difference in the size of the confidence intervals depending upon whether you were trying to estimate the score on Y for the sample and whether you were trying to predict an individual score. Now, one of the things that we did was we showed you about the 95% confidence interval, but what we didn't show you was the test that one uses in order to evaluate that 95% confidence interval, namely the t-test and the importance of the t-test. And then conceptually, the idea of the confidence intervals around the average or around the point estimate that is defined by the regression line. So let's move forward a little bit and do that. Okay, let's take a look at our estimates of the regression line. And so here we have our x-axis again and along our y-axis. And we have our regression line right here. Now, as we have run into before, we have an estimate. In this particular case, we have these points right here where the mean intersects with the regression line for each of these points along the x-axis. So what that means is that there is theoretically an infinite number of points along this regression line that correspond to the attribute of x. But have we measured this attribute of x with perfect precision? In other words, is this regression line a perfect association? Well, as we said earlier, no, it's not likely to be a perfect association. Hardly anything is measured with a perfect association. So what we have done is we are estimating this with a certain degree of error. And so if you look at this normal distribution, what we're looking at here is this is the possible range of values with a mean score here. of this value at the y-axis, at the correspondence between this point on the y-axis and this point on the x-axis. And if you also kind of take a look at this as a whisker on a 95% confidence interval, what you have here is the mean score and the 95% confidence interval around this estimate of the b at this point of x. And so there is an infinite number of these distributions around each estimate of x. And this is how this is calculated, is that you look at the standard error of this regression estimate, which is this right here. So if you look at this, this is sort of like a standard error of the mean. So you can look at this particular estimate in exactly the same way then as you would look at the standard error of the mean. If you look at the term underneath the square root sign, what you're looking at is the sums of the deviations in y, just as you would creating the standard deviation, divided by, in this instance, rather than n minus 2. So you end up having exactly the standard error of the mean. And then how do you calculate a confidence interval? Well, it's the mean score plus or minus 1.96 times the standard error of the mean. So with a regression equation, in order to calculate the 95% confidence interval of the standardized coefficient, you take the mean score of the coefficient, or in other words, the unstandardized coefficient, plus or minus 1.96 times the standard error of the regression estimates. It is exactly analogous to what you did with the t-score. And in fact, you use the same t critical value as you would with a t-test. So, in other words, with an infinite number of persons in the study, the t critical value is 1.96 for a 5% error and 2.47 for a 1% error, and so forth. You would find the value of that t in the t distribution in the tables at the end of the book. So if we look at it in another way, what we have is that this is each individual person's score. This is the regression. On the y-axis right here, this is the distribution of the possible effects. And so what we have here is one standard error. So the standard error of the estimate. This means that 68% chance of the value is within one standard deviation. What do we mean by 68% of the value? Well, here is the estimate on the regression coefficient. This then would be the mean. And then what we have now here is 2 standard deviations and 3 standard deviations around the points on this regression coefficient. So if you look at it visually, what you're looking at is a distribution around the mean score that can be expressed in terms of the mean score of the coefficient plus or minus a 95% confidence interval, just as you were able to do that with the t-score and most any other type of mean. Now, so how do we test the significance of that slope? Well, what we do is we use the same t-test as we've used before. In this circumstance, what we do is we say whether the t is equal to the unstandardized regression coefficient, or the b, divided by the standard error of the b. Now, we're not going to show you how to calculate that. That's not necessary, so get your hands off of the panic button here. All of that is shown in the computer printouts that you get with the calculations that we'll be showing you near the end with the SPSS printouts. And by the way, I've put them into an Adobe Acrobat document so that you can download those and look at them as I go through the SPSS printout. So sometime before we get too far along in this additional lecture, go ahead and download that. Alternatively, since the b is very similar to the regression coefficient, what you would do is, in order to calculate the t, you actually then can use the Pearson's correlation to calculate the statistic as to whether the regression coefficient is statistically significant. And with a lot of different math, what you would be able to find is that the b is equivalent to the correlation and divided by the square root of what we would find as being the standard error of the b coefficient. And this is how you would calculate that. So, in summary, what we have done is we have shown you two different types of confidence intervals. The first confidence interval, the one that we did at the end of the last lecture, was the prediction of a specific y, or a specific estimate of the dependent measure for the population and for the individual. So this is different than what we have just done. What we have just done is tried to show you the 95% confidence interval and the test of the significance of the unstandardized regression coefficient, or the b. So don't get them confused. One is trying to predict a specific y or specific value on the outcome variable based upon the unstandardized coefficient. And the second one is identifying the significance of the unstandardized coefficient using the t-test and the 95% confidence interval. Now remember, the clinical hypothesis is that the regression coefficient is equal to 0 or not equal to 0. So the thing that you're going to be looking for is 1, a t of greater than 1.96. You're going to be looking at a probability value of less than 0.05 for a 5% alpha error. And then finally, since the hypothesis is testing whether the regression coefficient is 0 or not, when you examine the 95% confidence interval of the unstandardized regression coefficient, if it is significant, that confidence interval should not include 0. If it is not statistically significant, or in other words, you accept the null hypothesis, the 95% confidence interval will include the null value, or it will include 0. So let's move along and let's begin to look at the assumptions of regression that must be met in order to finally accept the results. Well, let's take a look at the assumptions of the regression statistical technique, or the ordinary least squares. What we're looking at is, first of all, that the first assumption, and this one is really the least robust, or the one which is least able to be violated, and that is that the mean value of the population of y at a given value of x, in other words, thinking about it as the different positions on the regression curve at point x and point y, it has to increase or decrease in a linear fashion as x increases. So the slope is equal to the change in x and the change in y, but it must be a linear increase rather than a curvilinear or an S-shaped curve. Then also, for any particular value of x, the possible values of y are normally distributed. So what do we mean by that? Well, we have to go back to that one figure that I showed. And in this case, you can actually see both of these issues. So as x goes up, y goes up in a linear fashion. So as you can tell on this particular diagram, that the regression slope is linear. And what we said about for each particular value of x, that y was distributed in a normal fashion, this is sort of a visual depiction of what that says. In order for the statistical confidence intervals, the statistical tests, and so forth to work, the y values have to be normally distributed around the regression equation at each value of x. And then finally, the standard deviation of the population of y is about its mean at any given value of x is the same for all values of x. So in your textbook on page 205, they talk about the term homogeneity or homoscedasticity. Now this gives you a visual depiction of what we mean by homogeneity and homoscedasticity. In the far left-hand figure, you get a value where the standard deviation is about the size of each value of x, the same as it would be for any one particular value of x. And so you can detail this by looking at the residuals for each of the predicted values. And as you see, that most of them are between these approximately equal lines. So on the other hand, if you look at one that is not homogeneous or does not have the property of homoscedasticity, you see here it's much thinner, and as the predicted value continues to go up, then this also gets wider the further away that you get from the low values of x to the high values of x. That the standard deviation for each value of x is not the same. Here, these lines are horizontal to the predicted value. They do not go up or down. It remains horizontal. Here, it continues to go up or it goes down. So it is not the same at each value of x. The standard deviation is not the same for each value of x. And the third particular diagram is even worse. This shows that the line is curvilinear, and while it may be the same width, it goes up and down. In this particular instance, the standard deviation is not the same. It's not horizontal across here or across here. It does change in a curvilinear fashion. One of the most important... Whoa! There's Dr. Doug, the data dude again. Well, one of the most important pieces of information that you will get from the regression equation that allows you to determine the strength of the relationship between the x variable and the y variable is what they call the coefficient of determination, or the R square. Now, the R square is the value of the correlation coefficient. While it is a rough indicator of the goodness of fit of the regression line, the R square is actually a better estimator. And the coefficient of determination is literally the square of the correlation coefficient. So it's R squared. So the coefficient of determination then, what is it interpreted as? Well, it is the percentage of the variance in the dependent measure in all of the y-scores that is explained by the variance of the x-scores. Let's look at the conceptual meaning again of the correlation. Well, it is again 1 minus the sum of the deviations from the regression line divided by the sum of the squared deviations. So what that means is if there is no deviation, again, you have a perfect correlation, and then the variable explains all of the variation. In other words, it explains everything about the y variable and how to predict the y variable. Well, if it doesn't predict all of the variation, that means something else must be predicting some of the variation. And so that's when you have to begin to think about second, third, and fourth variables, in which we will talk about when we get to multiple regression. Now, the coefficient of determination then is the R, again, is the 1 minus the residuals versus the total variation. So what we mean is that the R square is equal to 100% of the variation minus the sums of squares residual divided by the sums of squares total. So these are the same sums of squares that we saw with analysis of variance and within variance. So sums of squares then, 100% minus the amount of error gives you the amount of variance that is explained by the particular x variable or the combination of x variables. So what's an example of an interpretation? Well, if the correlation between a person's age and their systolic blood pressure is 0.8, so the r is 0.87. The coefficient of determination, or r square, is truly the square of 0.87 or 0.76. This means that 76% of the variance in systolic blood pressure is explained by the variance in a person's age, and that we leave 24% unaccounted for, which is explained by a variable other than age. So if you think about it in terms of models that you will get with multiple regression, the higher the variable, the higher the coefficient of determination, or the higher the r square, it means that more of the variance is being explained by the model. And the more of the variance that is explained by the model, the more comfortable that you feel that you have a variable which is truly a cause of the dependent outcome. Well, Dr. Doug the Data Dude's down there, and so I really want you folks to listen up, because the r square and the interpretation of the r square is sort of the holy grail of multiple regression. If you're going to look at the utility of a regression equation, you have to understand the r square. Now that's an awfully big pill to swallow all at once. So, sort of what's the bottom line in all of that? Well, the bottom line is, for examination purposes, I am not going to ask you to be able to reproduce those formulas that I just showed you with regard to 1 minus the residuals and so forth. That's really not what I'm going to be asking you to do. I do want you, however, to really fully realize what the r square means, and that it means that the higher the r square, the more of the dependent measure that is being explained by the predictor variable. So bigger is better in this instance. And so if you had an r square of 1, which is the maximum, then what happens is that you can explain all of the outcome as a result of the x variable or the combination of x variables. Okay? And the r square ranges from 0 to 1. 0 means that the x variables or the predictor variables don't explain any of the outcome, and the 1 means that it explains all of the outcome. And the reason it doesn't go between -1 and 1 like the correlation coefficient is because you square the correlation coefficient. So if you have a negative and you square it, you come up with positive. So you're looking at the absolute value of the variance explained. Okay, so again, the bottom line is we're looking at the r square as a measure of the goodness of the fit of the model and the bigger. Okay, ladies and gentlemen, let's go ahead and get started on our data analysis example. And so let's think back to scenario number 4 that we started with. And the scenarios is a research study to evaluate the relationship between weight gain and blood pressure after switching from one second-generation antipsychotic to another. So in this instance, what we were looking at is patients who were on olanzapine for a period of 90 days or longer, and then they were switched to another second-generation antipsychotic. Now, the research question that we were looking at is, are you able to predict an individual's blood pressure change by measuring their weight change? So let's go ahead and look at this data analysis using the SPSS software program. Okay, well, let's take a look at our real-world example that we have. And let's go ahead and look at the scenario number 4. Now, scenario number 4 was looking at the change in weight and looking at the change in systolic blood pressure. So let's analyze this information, and we're going to go down and we're going to be looking at regression, and we're going to be using the typical linear regression. So now we're going to look at the change in systolic blood pressure from pre to post. Our independent variable then is our weight. And let's see, what statistics are we going to get? Well, we're going to, of course, get our regression coefficient. Let's go ahead and get the confidence interval. And we'll get the r square and the r squared change and the descriptives. And so we'll continue forward. Well, let's see what we get. Okay, here we have the same descriptives as we had before, a change in the pre to post systolic blood pressure of minus 0.71 and a change in minus 0.88. We have our correlation, our Pearson's correlation of 0.178. Okay, well, before we move on to the regression model, one of the first things that you have to do is to look to see whether the equation is normally distributed, as we said in the assumptions, and to see whether it's linear. So let's have you turn to page 211 of the textbook, and let's use that at the same time as we go through our example. The first thing that you want to see is whether the distribution is normally distributed or not. Well, in this instance, then, what we did was we looked at the histogram of the regression standardized residuals, and if the equation, if the data is normally distributed, what you'll have is a mean of 0 and a standard deviation of 1, just as you do in the z-score. Remember when we said with the z-score it's a standardized distribution? Well, that's what this means. And so you can see that the standard deviation is equal to 1 and the mean is equal to 3.5 times 10 to the minus 17th. Now, that's pretty darn close to 0 if you ask me. So far we have a pretty normally distributed distribution. So let me move down here, hang on. Okay, looking at figure 813 on page 211. What we're doing here is we're looking at an analysis of the residuals. And so if you look at the change in the systolic blood pressure pre to post, and then you look at the regression standardized residual, what you'll see is that the individual observations, which you see with the circles here, are pretty much in a straight line, just as the figure 813a would demonstrate then a relationship between x and y. So given these two pieces of information, I'm pretty confident then that we can move on and use the results from the regression analysis to help us make some decisions about whether weight and systolic blood pressure are associated. Okay, well, let's go ahead and move forward and look at the regression equations and the unstandardized coefficients and the model. What you see is we have here is our R, which is our predictor, our correlation coefficient of 0.178. If you square 0.178, you get an R square of 0.03. So this is a pretty long way from the 1.00, so there isn't a whole lot of effect of change in the weight on the change in the systolic blood pressure. The F change, and this is what we're going to be looking at in the next time about the statistical significance, is the F ratio with the change with 1 degree of freedom. And if you look at down here, you see, what do you see? I thought we were doing regression. I didn't think we were doing analysis of variance. Well, ladies and gentlemen, this is where I told you where analysis of variance and regression are very similar in the same generalized linear model. Okay, so you get the same information. You get this, in this case, rather than ANOVA, it says instead of the variance within the groups, it says the regression. It has the sums of squares, and if you think about it, that does make sense, given that we're going to have the individual person score minus the mean score for all 1,469 patients in this study. There is one variable, and that one variable then was the weight change, and so you then come up with the same mean squares estimate and an F ratio as you did before. And if you think about it, what made the variable significant, the critical value? Well, it was with an F in excess of 3.84. So as you can see, then with an F of 47, almost 0.9, that it was highly statistically significantly different. Okay, now this particular analysis of variance model and the F ratio here is very different than what we've talked about up to this point, and we'll talk about it more a little bit later on when we get to multiple regression. But the difference between the F ratio and the analysis of variance test and the t-test that we're going to talk about in just a minute is that the F ratio tests the whole model. So in this case, we really have only one independent measure predicting the the systolic blood pressure change. In multiple regression, we'll have more than 1 degree of freedom. So in this case, we are testing the overall model and the amount of variance, if ultimately that will be explained. What we're going to talk about in just a minute is the t-score. And the t-test, what it does is it tests the slope. It tests the significance of the unstandardized coefficient. And even more importantly, the t-test tests whether the slope is equal to or not equal to 0. And it helps you to test then the null hypothesis, whether to accept or reject the null hypothesis. The F ratio, the whole model, the t-test, the null hypothesis. So don't get those two things confused. The F ratio in this instance and the t-test test different things. The F tests the model, the t-test tests the significance of the unstandardized regression coefficients. Now I'm going to have to move this around a little bit, but let's go ahead and take a look at our regression coefficient table. And so what do we see here? We see the n-standardized coefficient from this variable of weight and change pre to post. Now what do we have here? Well, this says constant. And in the regression parlance, this constant then is the same as the intercept. So the intercept is at the point of minus 0.575, and it has a standard error of 0.483. Now, the change in weight pre to post has a B coefficient, or an unstandardized regression coefficient then, of 0.158, and it has a standard error as well. Now remember a few minutes ago when I said to you that I wasn't going to ask you to calculate the t coefficient because, the computer's going to do it. Well, I lied. Just kidding. Just kidding. Get your fingers off the panic button. And so what we see here is the computer has done that calculation. And I also said that what we're going to do is I wanted to show you that the computer in fact calculates the standard error for you. And there it is. This is what you would see then with regard to the standard error in the computer printout that you would get as a result of the analysis. And just to show you that it worked, if you were to take the B, which you see there as 0.158, and if you divide that by the standard error, which you see as 0.023, what you end up with is probably about 6.87, and this t here says 6.92, and they're the same within rounding error. So now we're going to look at the t-test, and this t-test, we'll get to it in a little bit later, but what it is the evaluation of whether the slope is statistically significantly different from 0, just as we showed early on with our clinical question. So in this instance, then, the slope is statistically different from 0, as you can tell then from this beta of 0.178. So I'm going to move this a little bit. Hold on to your stomach. Okay. Well, now what do we have? We have a unstandardized coefficient of 0.158. Now, we also then have a 95% confidence interval, and this is the 95% confidence interval for the B. The lower bound of the 95% confidence interval is 0.113, and the upper limit of the confidence interval for B is 0.202. So again, what does this mean? Well, it means that I am 95% confident that the true value of the slope for patients with a change in weight from pre to post and the effect it has upon their blood pressure is 0.113 to 0.202. That the true mean of this change, or the true mean, or the true slope, is between the lower bound and the upper bound of the 95% confidence interval. Now let's go back to this. What does this 0.158 mean? Well, it means that for every change in weight of 1 pound, there is a 0.158 change in the systolic blood pressure. So it's not quite a full millimeter of mercury. It's actually about 1/6 of a millimeter of mercury that the blood pressure goes up with every 1 pound increase in weight change. On the other hand, since the coefficient has a positive sign, in other words, it's not a negative 0.158, just as you see with the constant, but it is in fact a 0.158. That means it is a positive correlation. So when you have an increase in weight, you have an increase in the blood pressure. So if you have a decline in the weight, you have a decline in the blood pressure of the same magnitude. So if the weight goes down by 1 pound, you have a decline in the systolic blood pressure of 0.158 millimeters of mercury. So the positive, remember, the positive correlation means if one goes up, the x variable goes up, then the other, or the y variable, goes up. If the x variable goes down, the y variable goes down. All right? So this is how you would use a multiple regression equation to evaluate the change in systolic blood pressure that is predicted. Now remember, we're not talking about association now, we're talking about prediction with each pound of weight change from time 1 to time 2 when the patient was switched from olanzapine to another second generation antipsychotic. As the patients gained weight, their systolic blood pressure went up. As they lost weight, their systolic blood pressure went down. Now, we determined that there would be a change, and so the question is, as we look at the population, what is the average change going to be when a person changes their weight after the switch from one second-generation antipsychotic to another? So if we look at the general linear model, let's try and do a numeric interpretation. If you recall the structure of the general linear model, we have that y is equal to alpha plus the beta 1 times an individual score of x1 plus the error. So if you think about the result that we just looked at with the output, what we have is that the intercept was minus 0.57 plus the unstandardized regression coefficient of 0.158 times the individual person's score on the x-axis. And in this case, then, what we are looking at is the mean score. So if we were to have a score of, let's say a person gained 10 pounds of weight after switching from olanzapine to another one of the second generation antipsychotics, what you would do is substitute plus 10 for the x, and so the y would be equal to minus 0.575 plus 0.158 times 10, which equals an increase of 1.0 millimeters of mercury for a 10-pound weight change. On the other hand, if a person loses weight, so you would multiply the 0.158 unstandardized regression coefficient times a minus 10 for a minus 10 pounds. What you find is that the person's blood pressure would decline by about 2 millimeters of mercury. So this gives you a sense of how you would calculate a projection for the population of what the weight gain would be if a person were to increase or decrease their weight after switching from one antipsychotic to another. So what I would recommend that you do is that you try a couple of these yourselves. And so you could look at maybe a 15-pound weight change, a 20-pound weight change, a 25-pound weight change, and see what you come up with. And then what you could do is you could graph the weight change and the systolic blood pressure, and then you could look to see whether it is a positive slope or a negative slope and what that slope might look like. So give it a shot, see what it looks like. Let's go ahead and wrap this up for the simple regression. Now, why did I just go through that really long explanation of how you interpret the correlation coefficient and how you interpret the regression coefficient in making a decision about the relationship between weight gain or weight loss and blood pressure change? Well, I went through this particular set of data because it was ultimately published, as you can see here, in the Journal of the American Pharmacists Association by myself and a couple of my colleagues. Okay, now just a second, I'm going to move it around a little bit more, so hold your stomach while I change this. All right, well, let's take a careful look at this, and this is exactly the same question that we were talking about earlier, is what is the association then between weight change and blood pressure? Now, if you look at the correlations between weight change and change in systolic blood pressure, the correlation was approximately 0.19 or 0.18 milligrams of mercury per pound, and 0.15 for the diastolic blood pressure. Okay, so this is, within rounding error, exactly the same information that we showed you in the analysis that we conducted within SPSS. And so you can see here what we did was we then calculated out the change in millimeters of mercury per pound, just as we did in the interpretation of the linear model within the earlier part of the lecture. Okay? Now, also within the same article, what we tried to show you is another instance where we looked at those who gained weight and those who lost weight, and we showed that for those who gained weight, the systolic blood pressure increased by 4.2 milligrams of mercury, and for those who lost that specific amount of weight, then the diastolic blood pressure, it also declined by 2.1 millimeters, or excuse me, it went up by 2.1 millimeters of mercury. Okay, so why am I showing you this? Why am I showing you this? Well, because in the article, in most instances, all you're going to get are the regression coefficients or the correlation coefficients. And how that regression coefficient then is converted into a change in a certain number of millimeters of mercury is oftentimes not included in an article. In this particular case, we put it into this article because it is more, I think, impressive when you tell somebody if they lose a pound that their blood pressure is going to go down by 2.1 millimeters of mercury, compared to if they gain a pound, it's going to go up by 4.2. Okay? So this is the sort of thing that, as a reader of the literature, that you as an individual are going to have to make those kinds of calculations in your own mind or put them onto a piece of paper, but it's going to then have to really influence the way that you make those clinical decisions. So summary of today, well, what did we do? We looked at the 95% confidence interval and the variations around the estimate of the n-standardized coefficient by looking at standardized curves that were along the regression line. We talked about the coefficient of determination, or otherwise known as the R-squared, and its interpretation. As the R-squared goes up, there's more explanation by the variable or linear combination of variables. And finally, we looked at the linear regression analysis, the simple regression analysis example, and we looked at its interpretation both in the terms of the unstandardized coefficient, whether it was positive or negative. We looked at the 95% confidence interval and whether it included 0 or not, and that inclusion of 0 in rejecting or accepting the null hypothesis. And then we looked at a numeric example so that we could do some predictions of what the systolic blood pressure change would be like if we looked at some specific sizes of weight change within those different second-generation antipsychotics. So, as I said just a couple of seconds ago, it's really important that you understand these basic principles. So if you have any questions that we can answer for you, don't forget to post those questions on the discussion boards, and don't forget to post your muddiest points. So this is Dr. Doug, the Data Dude, signing off.